Hi, and thanks for joining me in this discussion of thermometry. And specifically, in this video, we're going to talk about temperature sensors. And temperature sensors can be categorized based upon how they work. What's their physical principle of measurement? How does it work? And we're going to look at two different kinds. We're going to look at thermal expansion and thermoelectric. In this video, we're going to stick strictly with thermal expansion thermometers. What thermal expansion means is that the materials that are used to make the thermometer expand as temperature increases and, of course, contract as temperature decreases. The first one we're going to look at, there are several actually, but the first one we're going to look at is the liquid in glass thermometer. The liquid in glass thermometer uses, of course, the expansion and contraction of a liquid inside a capillary in a glass, usually glass, to indicate changes in temperature. The two liquids that are used are typically mercury or alcohol, which is also known as spirit in glass thermometers. Mercury has a very high temperature, but also it has not such a low temperature range. It only goes down to about 38.9 degrees Celsius. So in some parts of the world, it may be difficult to measure low temperatures with mercury in glass thermometers. So in those locations, spirit in glass thermometers were typically used to measure low temperatures because the alcohol doesn't freeze until a temperature of minus 117 degrees Celsius. The thermometric fluid that's used, whether it be mercury or alcohol, expands based on this equation or this relationship. And it shows the change in volume of the fluid is equal to the initial volume of the fluid times beta, which is the differential volume of expansion, the difference between glass and the fluid, whether it be mercury or alcohol. Also, the change in temperature. So you'll have a change in the volume of the fluid based upon the initial fluid, amount of fluid, the thermal expansion coefficient, and then finally the temperature. Now that can be related to the capillary. In a liquid and glass thermometer, you typically have a very small capillary that has a small radius r. So the area of the capillary is pi r squared. It's a circle. And then multiply that by the change in height of the fluid in the capillary, and that gives you a volume, and that's the change in volume in the stem of the thermometer. We're going to rearrange this equation a little bit to get the change in temperature. So this gives you how temperature changes based on the initial fluid, also the change in height, the thermal expansion, and then also the size of the capillary. So if you know what the height change was, you can figure out the temperature change in the thermometer. We can further rearrange this equation to get the sensitivity of the thermometer, the liquid and glass thermometer. Sensitivity means that you're going to get a change in height of the fluid in the stem of the thermometer for a given change in temperature. So rearranging the equation that we have, now we have, as you see in the middle equation, delta H delta T. That's our sensitivity. How high does the mercury or alcohol go with a change in temperature? And that's related to V naught, which is your initial volume in the bulb, the thermal expansion coefficient beta, and then also the area of the capillary, pi r squared. So that is now the equation for sensitivity. And we're going to explore each one of these to figure out what makes a very sensitive thermometer. So to increase the sensitivity of a liquid and glass thermometer, you want to increase the values that are on the top or in the numerator of this equation, which are V naught and beta D. V naught is the volume of the fluid, the initial volume. In other words, the amount of fluid, whether it be mercury or alcohol, in the bulb or the bottom of the thermometer. The other thing that you can do is also change the thermometric fluid. In other words, go from mercury to alcohol or perhaps something else that expands even more than glass to give you a good change in sensitivity, a good increase in sensitivity. The other thing that you can do is make the things in the bottom of the equation, the denominator, smaller. What we have there is R, and R is the radius of the capillary, and the capillary is the little tube that's inside the glass that goes up the stem of the thermometer. So if you make that smaller, that'll make S bigger, meaning that a smaller hole in the thermometer stem, or the tube in the thermometer stem, the capillary, will increase the sensitivity. So of course, we use, in making liquid and glass thermometers, a glass tube. So we have to make sure that the capillary, the center in the glass, that little tube in the glass, is small and also uniform. We also have to make sure that the walls of the glass are thick. The glass has good strength. And also the walls of the glass actually help magnify the thermometric fluid, the height of the fluid, so you can make a good temperature measurement more easily. And of course, the glass bulb portion of the thermometer is the sensing portion of the thermometer. Want to make sure that the glass walls are as thin as possible. And the reason for that is because it will transfer energy from the atmosphere to the fluid, and you want the fluid to heat up or cool down with changes in temperature, and not so much glass but more of the fluid, because that's what is expanding and contracting. The fluid is going up and down. So you'll need to make sure also that that glass bulb is as thick as possible so that you have strength. It's very easy to break a very thin glass layer or a glass bulb. And of course, we saw from the equation that the size of the bulb determines the sensitivity, but it also determines how fast the thermometer responds. If you have a big bulb, as the equation saw, a big volume, a volumetric fluid, means you'll have a very good sensitivity. You'll have a big change in the height of the thermometer for a small change in temperature. However, the bigger the bulb, that means there's more mass, and mass takes longer to heat up. If you have a greater mass, it takes longer to heat up. So that'll slow down the response time. So increasing the size of the bulb increases the sensitivity but slows down the time response. Then also we talked about decreasing the size of the capillary within the glass. I had a mistake when I was making thermometers once. I got the wrong size capillary. I got a capillary that was twice the normal size, and I was trying to figure out why my thermometers hardly responded to changes in temperatures. And what happened is, after I looked at the shipping instructions and the shipping information, it dawned on me that I got the wrong size capillary. So smaller capillaries means you have greater sensitivity. You'll have a bigger change in the height of a fluid for a small change in temperature. However, if the capillary is very small, then it's really hard to read or figure out the height of the mercury or alcohol in the glass. Also, it's more difficult to build. It's really hard to blow a bulb in such a small capillary. And then also the fluid tends to break more easily. Break meaning that you'll see gaps in the fluid, believe it or not. So here's some numbers for the coefficient of volumetric expansion for different types of materials. And of course, the thermometer is made of glass, so you can see that its expansion is, volumetric expansion is 2 to 3. But compare that to methyl alcohol, 140. So you can see that methyl alcohol changes quite a bit more than glass. Whereas mercury, the coefficient of volumetric expansion is actually much smaller. It's only 18. So you don't get a big change in height with mercury as you do with alcohol. Alcohol changes more. So to summarize, mercury is probably the most accurate, but alcohol is the most sensitive. Also, another advantage to mercury is that it's stable. Alcohol is unstable, meaning that if it heats up, it can cause gaps, and also it can adhere to the glass surface, which causes problems. Glass surface inside the capillary, meaning that you'll have breaks in your thermometric fluid, and that's not good for a thermometer. So those are the basics, the basic theory behind a liquid and glass thermometer. I hope you enjoyed it.